Thank you. First of all, good afternoon, ladies and gentlemen, dear colleagues. Thank you for inviting me for this exciting conference. And as you can see, I am the first speaker today who will not be talking about experiments. So what the core of our business in the really new established group are simulations, in particular molecular simulations. But let's see why do we use simulations and why are simulations useful. As you can see here, they can be used in many spheres of our lives. For example, we can calculate what will happen if two galaxies collide in millions of years. We can try to predict what the weather forecast, this one is very nice, by the way, will look like at some point of time. We can go to very short time scales and small space scales and talk about, let's say, atto-femto processes, collisions of gold. Atoms here, for example, presented, but the core of our work is actually about molecules, and it's shown here, right? So what we are trying to do are molecular simulations which occur roughly at the time scales of pico to milliseconds. So what is the idea of our simulations and what our molecular simulations can actually do and how can we use them in chemistry? First of all, simulations have some advantages which experiments do not have. The first and the most important one is that they can predict something. Whether this is correct or not is another issue, but they can predict the future. Very often, we cannot, from experiments, get all the molecular details we want, but with simulations we can do it. And very often they're also more affordable than experiments and cheaper, although this depends on the scale of the simulations. Simulations can very easily be connected to experiments, as you can see here. For example, if you have some model experiments, spectroscopic and so on, this connection is quite easy between simulations and experiments. However, connection between simulations and applications, which is also done here at this university, is more tricky. However, we think that by using new techniques like artificial intelligence, machine learning, we can propose maybe some risky experiments which can lead to unexpected applications. We can maybe provide some new ideas, new insights in things. And finally, the connection between experiments and application, it's not so obvious how simulations can help. But usually between experiments and applications, you do not have a full molecular picture, which is missing. And here we can try to connect these things, at least by simulating at some other scales. I will show just two case studies which we are doing in our group. First one is about arginine-rich peptides, which are used here and shown here. And these are the compounds which contain a lot of arginine amino acids. And these arginine amino acids have something which is really interesting, and these are these guanidinium cations, which are two cations which are positively charged, and instead of repelling, they attract to each other in water. And this property actually is transferred also to arginines, which contain these guanidinium side chains. And this property actually leads, and we are interested in how it is connected to the very easy penetration of these arginine-rich peptides into the cell, in which way we can deliver something like a drug into the cell. The other case study which I would like to show you is more connected to the endosomal drug delivery, which is also directly connected to the previous one, because we have found that specific combination, in this particular case guanidinium-rich cationic peptides and specific lipid, in the course of normal endocytotic process, how the drug is actually digested by cell, involves one step which is called endosomal escape, where two cells, actually these two small vesicles, fuse and release the drug. And we can explain the molecular details of this process. If this looks familiar to you, this is exactly the same principle which is used in COVID vaccine. For example, either Pfizer, either Moderna, where the critical step when releasing the RNA or drug or anything is this endosomal escape. And this endosomal escape can be described with molecular dynamics at really good level of theory and good details. So, taking these two study cases into account, I can envisage many possible interdisciplinary connections here with people who do either experiments, either applications. So, for experiments, anything from spectroscopy up to the electrochemistry can be actually used by molecular simulations. Machine learning, drug delivery development can be used in connecting simulations to application. And as I said earlier, we can also try to connect and to make the full circle all of these aspects in molecular simulations by connecting these techniques which I just explained. And with this, I would like to thank you.
Thanks a lot for the great talk. Questions? Okay.
It's more like a comment. I think you're the first one I have not saying that connecting the experiments into simulations is easy.
It's easy. That's difficult to say it's easy. It depends what kind of experiments. If experiments are relatively easy to understand, and if they are connected to the molecular picture we can easily simulate or understand or calculate, then the connection should be easy and should be one-to-one, if quantum chemistry or whatever we are using is correct, right? But if the experiments, the real situations, organic catalysis or something else, where a number of things occur and we have them in the system, then of course it can be more complicated. But if nothing else, it cannot be always quantitative, but definitely qualitative answer. Maybe even in, for example, your applications could be achieved easily. Yeah.
Okay, thank you.
Lots of things may happen, especially in biological systems. So concerning these systems, you know that the very important molecules are not just a separate cells, organelles, or compartments, whatever, but also ions and water molecules. And I know that in simulation it's pretty hard to predict or simulate these things in complex. So how far is it now?
You mean in terms of including water and ions and stuff like that in simulations?
Yeah. For instance, if you have molecular interactions or
now we are very well advanced into this. So we include always water in our simulations. We always include ions in simulations. What we cannot still, for example, control, which would be a very, very good aspect, is pH and very small differences in pH. Because differences, for example, between pH of 7 or 6, you need 10 million water molecules to see the difference, because one will have proton, the others will not. So these are maybe two big systems still to catch. But ion concentrations, peptide concentrations, we can control that. We can control water. We can solvate everything quite nicely in the systems we have. But very subtle effects on which biology actually is based on, it's still quite far away. But qualitatively, we are going in this direction.
Thank you.
I have to say that I'm quite not satisfied with the kind of draw, because from my point of view, the experiment and the model simulation are quite very welcome. From my point, modeling or simulation is something like the computational experiment. So it's kind of experiment. But okay. The question is how to validate the outcome from the modeling and simulation.
Okay.
One method.
Of course, we need experiments. So for that's why I actually, if I may, simple experiments. And that's why I divided simulations and experiments. Of course, simulations are computational experiments. That's absolutely true. I mean, it's a buzzword these days that you have computational microscope. So this is a known thing. However, we can set up relatively simple experiments and connect them to the simulations, for which, for example, we need some parameters for them to be true. And these connections, to get the good parameters for simulations, we can connect with simple experiments to get the parameters and validate them, because we can from simulations even, for example, thermodynamic quantities or some other quantities, we can get almost one-to-one. So we can know that our parameters which we are using in one system, we can validate in the as close experiment as possible to our system which we are simulating. Since now these days, we can simulate larger and larger systems, so we can really connect, we can really make this small experiment containing, I don't know, 10 to 18th water molecules and simulations with 10 to 10 water molecules. So we're still not one-to-one, but we can get through and we can get the parameters we want comparing to simple experiments. And that's actually what is used for validation mostly. Either X-ray structures or thermodynamical parameters or whatever. This is how we check our experiments. Yeah.
So time is running, so please thank the speaker again. And our last, but of course not least speaker from Faculty of Food Bio.